main goal today is to make sure you guys are good with these, all right? For sure, you have to walk out of the room completely understanding forwards and backwards number 1, all right? Like problem number 1, A through whatever it was, W, all right? Like I say, this stuff is going to get harder, and if you can't do number 1, you're going to struggle, okay? So if there's anything you don't understand about it, please let me know. I already had a request for number B, and I stand by that terminology, number B. So I want to go over that one to make sure you guys understand normal force, and then if people have other ones, please, let's do that. And then we should probably at least quickly talk about number 2. I don't want to get too worked up about it. And then I know we need to go over number 7. So those are the ones that are on my list. All right, so let me do 1B, and then Simon, what do you got?
I just had a quick question about 1A.
Okay, yeah, shoot.
Is the force of gravity supposed to be negative?
Did I not put negative on it? So a lot of times when I make my free body diagrams, you guys, I never used to put any signs on my free body diagrams because the arrow tells you the same thing as the negative.
Yeah.
So I'm trying to get better about it, but I occasionally forget, and that was one where I forgot.
Okay.
So yeah, if it's downward, it's negative, always, without exception. Okay, and if it's up, it's positive, always, without
It's the
exception.
same for left and right.
And same for left and right, yeah. And in fact, there's one other one where I had a, I'm going to steal this for 1 second, Savannah. What's that? Where's the EFGHI? On letter I, that net force should have been negative also. So there's a couple little things here and there. Sam?
On the test, if you don't negative.
As long as you have if you're missing a negative on a drawing, but then use the numbers correctly and get the right answer, you're good. Do you know what I mean? Yeah. Okay. All right. Any other general questions? All right. So let's run through this. So first of all, normal force. You absolutely have to understand normal force. All right. Common misconceptions. First of all, please do not make the mistake of thinking that normal force is always equal to gravity, because it's not. Okay? Secondly, don't just completely ignore your normal force, because it often has to be there to prevent your object from moving down through the floor or whatever it's sitting on. Okay? So, let me give you guys a real quick, it's kind of a silly demo, but I think it sort of highlights how normal force works. Okay? So, Garrett, do you mind if I pick on you?
No.
Yeah, come on up for 1 minute. I need to find something that's not so bulky as this. All right. So I want you to put your arms out. You're going to be our table. You're just going to do this, okay? So he is our table, right? Okay. So here's our object. You got it? Okay. So right now, gravity's pulling down. Let's suppose that this is the problem in number 2. Okay. So gravity's pulling down with 750 newtons. Okay. So he's going to get tired. He's going to get pissed off at me soon. Right now, he's pushing up with 750 newtons, right? Can you feel that?
Yeah.
Right? So he's the support force. He's our normal force, right? Okay? Now I decide I'm going to lift this thing, because Frank, my son, wants his Hot Wheels tracks back, right? And I'm not very strong, you guys have seen, I'm kind of scrawny, right? And I come along and I go, eh. All right? So I'm lifting up on it with, I don't know, 400 newtons. Tell me what you feel.
Less force.
Yeah. He's exerting less force, right? Why? Because I'm supporting some of it, right? So now, originally, he was supporting all 750 newtons. When I come along and lift with 400, now he's only got to fill in the remaining 350 or whatever it is, right? Cool? There's a problem later on the worksheet where somebody comes along and pushes down on it. So what does he have to do now? He's got to push up with more force, right? Follow? Okay? But in all of those cases, what are the up and down forces basically doing? Canceling each other out, right? And as long as you're just talking about like a table or a floor or something, that's going to be the deal. The forces cancel out. Okay? The weird exception is number 2, where the floor in an elevator actually does lifting for you, right? Okay? Does that make sense?
Yeah.
Okay, cool. All right. Everybody, does that make sense? Thanks, Garrett, for doing that. I know that was awkward. Okay, so with that in mind, let's run through number 1B. So 1B says, a man uses a force of 400 newtons to try to lift a 750 newton cabinet. So here's the cabinet. Step 1, every single time you make a free body diagram, you start with mass and force of gravity. I'll always give you one, you find the other. So here, it's a 750 Newton cabinet. Is that mass or weight? It's the weight, right? So put it in your drawing. That's an arrow. So there's our force of gravity. Good? How do I find the mass? Where we got time?
Effective force divided by acceleration.
Yeah, divide the force by what acceleration if we're trying to find mass, you guys?
Gravity.
So 9.8, right? Okay, so it gives you, what is it, 76.5? All right, so there's that. So that's always step one, mass and force of gravity. Good? Step two, any given forces. So this problem tells you that there's a force from some man lifting this thing with 400 newtons. Good? And then step three is, and I don't mean this in a snarky way, but you have to stop and think. All right, a lot of times I get people, they just sort of like in autopilot, and they go, oh, cool, well, I figured out gravity, he gave me the force of the man, let's find the net force. Oh, the net force is negative 350. And then they get a weird negative acceleration. But that doesn't make sense, because then my cabinet would be going down through the floor. So you got to think. So he's trying to lift it. Does he succeed? No, because the 400 newtons isn't enough. So you go, oh, it's not going to move. Oh, that means the net force has got to be 0. Then you can find your normal force. How much force does the floor need to prevent the cabinet from going down through it? And so, yeah, it's got to be 350. Let me say one thing and then I'll get your question, Garrett. So I know a lot of you are able to just go, oh, it's got to be 350. And I want you to remember that you also have this little trick of solving for a missing force. Right? We know our net force is 0. We know the force of gravity is negative 750. We know the force of the man is 400. We don't know our normal force. So solve for it and it gives you 350. Okay? Particularly as the numbers get more involved, sometimes you won't know what direction a force is in, and writing it out this way will make it easier for you. What do you got here?
So the only reason there's not a normal force in C is because they get it off the ground.
Yes, because in C, how much force does he exert?
900.
So what's special about 900 newtons as compared with the 400?
It like overcomes the gravity.
Good. It's enough force to lift it, right? Make sense, you guys?
Yeah.
Good questions. All right. Any problems with 1B? We're good? All right. What other problems from number 1 do we need to look at? There was walking around, I saw a lot of people marking them up and making little corrections and stuff, so let's ask questions if we got them. No? Can we go on? Okay. All right, so number 2. So in 1C, real quick, this is going to tie in. So in 1C, the idea is your gravity is 750, and the force from the man is 900 newtons. There's no normal force because he's going to succeed in lifting it, right? So you get a net force of 150, and then based on that, you can find your acceleration, right? Everybody good with that? Okay. Number 2 is the exact same thing, except instead of a man lifting a thing, it's an elevator lifting a man. Okay? Does that make sense? So the idea is, weirdly, in that situation, here's the floor of the elevator, here's the dude. Hello. So the idea is gravity is pulling the person down with a force of, I think it's negative 836, if I remember right. Isn't that the weight of the person? Okay? So when they're on the ground floor, the normal force would just be 836, right? Is there, maybe that's not clear. Is it not clear why the weight is 836?
85.3 kilograms.
Which, if you multiply by 9.8, gives you
Oh,
this.
right. You're talking.
Yeah. Good?
Yeah.
Okay. So, sorry, I realized I glossed over something. Let's talk about bathroom scales for a minute. All right, well, that's a weird question, weird statement. Am I right? Isn't this?
Yeah.
Yeah, okay. All right, so here's the deal, you guys. Bathroom scales don't measure your weight. They measure normal force. All right? As simple proof, I'm looking, where the hell did I put my sheet? That's yours. Why would I? No, I want my sheet. Why did I don't know. I don't even know why. I don't even need it. I'm just bothered that I lost it again. Again, I always lose my stuff. Sorry guys, I'm having a rough day. Okay, so anyway, all right, so bathroom scales. Sorry. Bathroom scales don't measure what you weigh. All right, as simple proof. So when I stand on a bathroom scale, it measures about 150 pounds because that's what I weigh on a good day. All right, so I'm standing there, gravity's pulling me down with 150 pounds, the scale pushes me up with 150 pounds, right? Okay, so let's suppose Julian comes over and he pushes down on my shoulders. Okay, maybe he pushes down with a force of 20 pounds on my shoulders. What's the scale going to read now? 170. Do I suddenly weigh 170 pounds? No, I still weigh 150, right? Okay, so why does the scale read more? Because it's got to push harder to prevent me from going down, right? Because Julian's adding this extra force, right? So my weight didn't change, just the normal force changes. Does that make sense? All right, so if this dude who weighs 836 newtons takes that bathroom scale onto the elevator and stands on it, when the elevator's lifting him, doesn't it need to exert extra force to make him speed up? Right? And so the reading on the scale is going to go up, right? Does that make sense? Okay, so there are basically 5, I guess, different intervals that you need to be conscious of. First of all, anytime the elevator is a constant velocity, either not moving or moving at a constant velocity, what should be true about the reading on the scale?
Normal.
It should be 836, right? Why? Is the acceleration 0, so we need, and that force is 0, so this force has to cancel that, right? Okay? Now, anytime you're accelerating upwards, which force should be bigger? Gravity or normal force? Normal force, right? So it's going to read more than what you actually weigh. All right? There are 2 times when you are accelerating upwards. Okay? The first time is when you begin moving up at the bottom, right? Okay? And the second time, this one's weird, is when you get, like, suppose you're coming back down, when you stop at the bottom. Right? Because think about it. If you're moving down, if you want to stop something from moving down, point for me. Which way do you have to push it? Up, right? So when you get back down to the ground floor, the reading on the scale is going to go up again, right? Follow? All right. So let's think about that for a minute. You guys have all experienced this, whether you've thought about it or not. Think about what you feel like when the elevator first starts moving up. Don't you feel like you're like squished? You guys know what I'm talking about? And then when you get down to the main floor again, same thing. When you stop at the bottom, it's like, right? Because your body's still moving down and the elevator's trying to stop you. Okay? Adrian?
I don't know, you explained it kind of there, I understand.
You sure?
Yeah.
100%? Okay. All right. When are you going to feel lighter? When is the reading on the scale going to go down?
When we're slowing down.
No, we just said
Acceleration's
when the acceleration's negative, which happens twice. When you get to the top floor and stop moving up, right? Because your body's still moving up and the elevator's slowing down underneath you, right? Or when you start going down, right? Because the elevator's kind of dropping out from under your feet a little bit, right? Does that make sense? All right. Questions on that? All right. So then, as far as solving the problems go for number 2, you're given the normal force, and you know your mass is 85.3, is that what you said? Whatever it was?
Yeah.
So you can find your net force and then divide by the mass to get the acceleration. Good? All right. Any questions about number 2? Okay. Number 3 is a dumb question about a train that I should delete it because it's a dumb question.
Trains aren't dumb.
What'd you say? Trains are what?
Are never dumb.
Okay. Sure. I don't have a strong enough opinion. I don't have a strong enough opinion about trains one way or the other to argue that. All right. I want to talk about problem number 4, tension. So I just briefly discussed tension in the video, but I want to clarify something about it. Okay. And doing that will require me to find my stuffed bee.
It's on the trigger.
Ah, thank you. I never would have found that. Thank you. Okay, so look, you guys. So in number 4, it says that you've got a mass of 5 kilograms. All right, so check it out. Pretend the bee is 5 kilograms. All right, do you guys agree we can find the force of gravity on him?
Yeah. Yes.
5 times 9.8, so 49 newtons, right?
Yes.
Right, so suppose I did this. So if I hold the bee, gravity's pulling him down with 49 newtons. What am I doing? Pulling him up with 49 newtons, right? All right. Basically, all a rope does is it allows you to pull something without touching it, but it doesn't change the force. So right now I'm pulling up with 49 newtons. Right now I'm pulling up with 49 newtons. But I'm pulling the string, and the string pulls the bee, right? But still 49 newtons, right? So in this scenario, we say that the tension in the rope is 49 newtons. Because the string is exerting 49 newtons to prevent the bee from falling. Follow? All right, now, here's where people get messed up. All right, suppose I give one end of the rope to Julian. Julian, take the rope. All right, and we both pull on it with 49 newtons. So Julian's pulling that way with 49 newtons, I'm pulling this way with 49 newtons. What's the tension?
0.
Okay, so there's 2 common answers I get. Thanks. So common answer I get, number 1, is 0. That's the net force on the rope. What's the net force on the rope here?
Oh, no, 0.
The net force on the rope is 0, right? Okay. So in that example where we're both pulling it, the forces don't sort of cancel. Okay. They also don't add up. Was anybody thinking, oh, well, 49 at both ends for a total of, what, 98? That doesn't work either. That doesn't work either. Look, you guys. The string is pulling the bee up with 49 newtons, right? So we haven't done third law yet, but that also means that the bee is pulling the string down with 49 newtons. What am I doing to the string? Pulling it up with 49 newtons. So there's 49 newtons up, 49 newtons down. The tension's 49 newtons. Just like the tension's 49 newtons. If we're both pulling with 49 newtons, then the tension's 49 newtons.
What if you're pulling it different?
What if we're pulling with different forces? It turns out you can't. Okay? It's physically impossible. Okay? And I'll set up a demo to show you guys why a little later on, but not until we do the third law. Okay? Follow? Alright, so.
Wait, how could you not pull two different, like, what if you're playing, like, like tug of war?
Yeah, it turns out that the force at both ends of the rope is always equal, even in a tug of war. It's just that because there are other forces besides the rope. So here's the crappy drawing that I made for my 5th hour. See if I can find it.
Is it like with elastic?
Oh.
Oh no. We're getting it. Oh, there we go. Okay, so look. Shh. All right. So again, I don't want to get too bogged down with this because honestly, we need to know the third law to completely understand tension. But just kind of get you thinking about it. So here's the deal. We got a tug of war with 2 people. Very boring tug of war. Okay. So what I want you guys to understand is there are more forces on each person than just the rope. Okay. So the idea is this dude down at the end is pulling on the rope with 100 newtons. The rope acts as a conduit and allows this guy here on the right to pull the guy here on the left to the right with 100 newtons, right? So that's this. Good? Now, hopefully he doesn't move. If he doesn't move, what's preventing him from moving? The friction, right? So that guy doesn't move. All right? Now, it turns out that the tension at the other end of the rope has to still be 100 newtons. So there's also 100 newtons on this guy. If he doesn't move, what prevents him from moving is friction. But maybe there's not enough friction, right? And so then that guy is going to move a little bit, right? And then this guy has to draw in the slack to maintain that force. Okay? So long story short, if I'm losing you here, don't stress about it too much. There are more forces on the two ends of the tug of war than just the rope. Okay? Does that make a little bit of sense?
Kinda.
Kinda? No?
Not really.
No.
So, like,
We'll talk about it more when we get to the third law.
I highly disagree.
All right. So for now, I'm going to just ask you to take my word for it. The tension at each end of the rope is always the same. Cool? Cool. All right. We will, I promise we'll come back to this. We will revisit this. All right. So I think the last thing we need to talk about then is number 7. Yes? Is that cool? So number 7. All right, so on the answer key for number 7, ugh. All right, so on the answer key to number 7, I made a couple drawings. So on the answer key for number 7, I made a couple drawings. So there's drawing A is the dude preparing to jump. So we called that drawing A, right? Okay, so that's this. He's getting ready to jump, right? Now the problem tells you that he crouches like 0.2 centimeters before jumping. So between here and here, he's pushing his body up 0.2 meters. Okay, so the next instant we care about is this moment. Oh my gosh, what just happened? Game of Thrones? Oh. All right, so that's the moment when he's just about to leave the ground. All right, and then he jumps. So eventually he's up here in the air. So that's drawing C. Good? All right, so look. So the problem tells you that between here and here, he kind of moves his body up through a displacement of 0.20 meters, right? And then between here and here, he goes up through a displacement of 0.80 meters. So does all of that make sense? Okay. So, let's see what we can do about coming up with some information about velocities. Do I know the velocity at any of these points on my drawing? 0 where? The velocity here is 0. I agree with that because he's just getting ready to jump, right? Bless it. All right, where else? In C, the velocity is 0 too, right? Because that's when he's at his highest point. But we do not know the velocity here, right?
No.
Good? All right, what about acceleration? So when we talk about acceleration, we're talking about velocity changing. So now we need to be thinking about an interval. So do I know the acceleration that he has while he goes from A to B? No, I do not know this acceleration. Let me do it, and let me do this. All right, how about over here from B to C? Do I know the acceleration there?
No.
Yes.
What?
Yep.
Oh my.
Gravity.
Why? What is it? It's free fall, right? After his feet leave the ground, the only force on him is gravity, right? Does that make sense?
Yeah.
Okay. So, do you guys understand why point B is so important? What's changing at point B? So the acceleration changes. Why? What causes the acceleration to change? The forces change, right? What forces act on him from A to B? There's 2 forces on him from A to B. Gravity and the normal force from the floor, right? Does that make sense? Okay, again, this is kind of third law E, so I'm sorry that some of these questions keep bringing up the third law. But the idea is when he pushes the ground pushes him. That's why he's able to jump. Okay? All right. So I feel like finding this velocity at point B would be useful. Don't you think?
Yes.
Right? Because basically what we need to know is what velocity he needs to leave the ground at to jump up 0.8 meters, right? So let's do that. So for the red time interval, going from point B to point C, here are the things I know. I know the displacement is 0.80 meters. I know my initial velocity is unknown. I I know my acceleration is negative 9.8 meters a second squared. And I know my final velocity is 0, right? Good. So I think we can use this guy to find that VI, right? Follow? So if you do that, that VI ends up being 3.96 meters a second. And that number is of significance because it represents the velocity he has to have when he leaves the ground to jump that height. Questions? Okay, so now let's do this. No. All right, so now from A to B, what's the stuff we know? Well, we know that our initial velocity is 0. We know our final velocity's got to be 3.96 because that's the number we just found. We know our displacement is 0.2 meters, and we have to find the acceleration. Right? The goal is between here and here, he needs his velocity to get up to 3.96, and he's got 0.2 meters to work with. So, use this guy again. And find your acceleration. And if you do that, you get 39.2 meters per second squared. We are almost done. Are there questions with all that? Any problems? Okay, so now the last thing we got to do is figure out how much force is needed to make all of this happen. So, here's the deal. While he is in the process of, whoa, what just happened there? So while he's jumping, there are two forces acting on him. Name them. Gravity. We know his mass is 66, so this force of gravity is negative 646 point, is it 2 or 8? 6.8 newtons. So there's your force of gravity. Cool. We know the acceleration. What should I do with it? Use it to find the net force. Always. If you know the acceleration, find the net force. If you know the acceleration, find the net force. So here's where I went wrong on my answer key. 66 times 39.2 does not give you the number I said it does. It gives you 2587.2 newtons. So is that the answer to the problem? No, that's the net force. So now to find my normal force, we're going to do normal force plus gravity equals net force. Let me write it out. Net force equals gravity plus normal force. So let's see, our net force is that 2,587.2. That's got to equal the gravity, negative 646.8, plus something. And solve it. And the normal force ends up being 3234. Newtons. Cool, you guys? All right. So we're starting to run into the point where things are starting to kind of run into each other concept-wise. So we'll get the third law and we'll get friction. Those are the last two things we need to learn about. All right. Tomorrow we're doing a lab. Did I say this to you guys already? You can't do the lab if you haven't watched the video. All right. I'm going to check the notes. Got to watch the video. All right. Video 3.6 is due tomorrow. I will be checking the notes. We'll do the lab. When you're done with the lab, you can work on worksheet 3.6.
Soccer game tomorrow. The first 7:30 tomorrow morning. We'll have a spot on Santa Claus traveling to the boys' side. The walk will start at 8:30 and return immediately after the game at approximately 7:30 to 8 p.m. Again, the first 45 people.
Where's the game tomorrow? Anybody know where the game is tomorrow? Bloomfield. Okay. Maybe. I'll see you there. That's okay. We are looking at a test next week. Wednesday, Thursday, or Friday. The last topic we're doing is video 3.7, which is due Friday. Yeah. Oh, okay. Yeah, that's fine. I mean, it's another computer lab, so you can do it on any computer in the building, you know, or even if you have one at home, that's fine. Obviously, if you're here, it's better. So let's wait to see who else is out tomorrow. Hopefully there'll be something to pair up with on Wednesday. Good? Yeah, that's yep. And also, if you're struggling with those three-body diagrams, this week find the time to come in before or after. Let's work on that, okay?
Like when you explain it all out, like part of it is just like I don't like understand when it's being worked. I have no like I'm broad out. Once I have all my like
I got you. Okay. All right. Well, let's do some practice problems and make sure you're good. Cool? Yeah. What's up, Zach?